All right, so this is going to be how EKGs work, kind of my way. She did a really good job today though, so I don't know if this video is needed, but I thought I'd make it just mainly for myself to remember everything and maybe to help some of you out if something wasn't clear. So the first thing we'll go over is the action potentials in each of the two types of cardiac cells that we're dealing with. So I'm not going to go into the specifics of each channel, and like the calcium channels have specific conformations and stuff like that. Go back to the lecture slides for that because it just takes too long to get through all this stuff. And it's fairly straightforward in the lecture slides, it's just memorization. So in a cardiac myocyte, which is just a muscle cell, we have a specific action potential that's going to induce contraction. So in this one, what's going to happen is we're going to get a signal from another cell because the cell passes them to each other, between each other in intercalated discs. So they got like gap junctions between each other so they can pass this message on really fast. The first thing that's going to happen is we're going to have a massive sodium influx into the cell. So sodium channels are going to act open, just like in an action potential in a neuron. And sodium is going to flow in, and the cell is going to rapidly depolarize. I mean, really rapidly. And then what's going to happen is we're going to kind of get a stop to that. Okay, so all the sodium that wants to come in has come in, and those channels are going to close. And when those close, that new membrane potential, that depolarized membrane potential we have, is going to trigger these calcium channels to open. So the calcium channels are going to let out potassium channels are going to let out potassium out of the cell. So once this reaches its final depolarization up here, the potassium channels are going to open up and potassium is going to get out of the cell, okay? And it wants to do that because it has a higher intracellular concentration. Now, this, the efflux of potassium is going to be corresponding to our kind of downward portion of our action potential. But then, as you notice, it's kind of prolonged, like it doesn't go straight down like a normal action potential would. And that's because we have another type of channel opening at the same time, or just shortly after these potassium channels are opening up. We have our calcium, our long type calcium channels. They're named long because they stay open for a long time. And these long type calcium channels are going to be responsible for letting calcium into the cell and keeping it depolarized, okay? So that's why we get a long kind of plateau. And after a while, these calcium channels will close off, okay? So they stay active for quite a little while comparatively, and then they're going to close off. Well, these potassium channels are staying open, and potassium is continuing to travel outside of the cell. But we don't have calcium coming into the cell, so we are now going to be hyperpolarized because there's nothing opposing this potassium and its charge from leaving the cell. And that's going to rapidly repolarize the cell to its resting membrane potential. Simple enough, right? Well, our nodal cells, which are our pacemaker cells, go on by a little bit different method. So they have these sodium channels, but they're not exactly like the channels in our cardiac myocyte. They're a little bit funny, and she calls them funny sodium channels. So these sodium channels, they're going to slowly let in sodium. Very, very slowly. And it's going to be a gradual influx of sodium into the cell until we reach a certain point, and that point's right here. And when we reach this certain point, it's going to induce these calcium channels to open up and rapidly depolarize the cell. Now in a nodal cell, we do not have our long type calcium channels. We just have one type that's kind of akin to the way that sodium enters the cell in a cardiac myocyte. It's just going to dump it in. Calcium is going to come rapidly into the cell, it's going to depolarize it, and we're going to get an action potential. And then when it's done influxing, these are going to close, And then potassium is going to exit the cell so that we can be repolarized again. And now, just like in all of our other cell types, we've got the sodium, potassium, ATPase pump maintaining our resting potentials. So we got 3 sodium out, 2 potassium in with ATP, right? All right, so EKGs get kind of hard. So we think about these and we look at the kind of waveforms on the graphs of how each action potential is moving. And we think, well, why does, whenever I see an EKG, it look like this? Why doesn't it look like that? Well, it's just a matter of perspective. It does look like that if you're measuring it from one cell, and you're measuring it, if you stick a probe right into the membrane of the cell, it does look like that. Because you're measuring it just from the ions moving in to moving out. But if we go outside of the cell, we get multiple cells lined up, we're only going to get the direction that the charge is moving, or the direction that the electricity is moving, okay? So the reason that this looks differently is because when we get a action potential coming towards a lead, or one of these electrodes that are stuck to us, when it comes towards it and it's the positive end of that lead, we're going to get an upward deflection. So all this means is, instead of us having these deflections based on the ion channels, we only care about which way is the electricity moving with an EKG. Which way is it moving, okay? And if it's moving towards us with whatever lead we're talking about, the graph's going to go up. Like right here, our P wave goes up. If it's moving away from us, it's going to go down. And the way we look at the heart is going to determine which way the waveforms are going to move, whether they're going to go up or down or left or right, yada yada, okay? So just a quick review of our conduction system in the heart. This was kind of glossed over, and I feel like most of us have had it in physiology in undergrad, so, but it's good to review. And really, if you understand the way things get conducted within the heart, the way electricity normally gets conducted in the heart, it makes the way to understand the pathophysiology, or the ways that it can go wrong, so much easier. It makes understanding arrhythmias and blocks and all that just so much easier if you can understand the basic premise of the conduction system. So like we went over yesterday, we've got our SA node. Now our SA node is called the sinoatrial node, and it is up in our right atrium, okay? And it's going to be our conductor of this system. It's like the conductor of the orchestra. And it's going to tell all the other cardiac myocytes and all the other nodal cells when to fire. Okay. So this usually sends out an impulse about every 60, or it sends out like 60 to 100 impulses a minute. So that's why we get the normal resting heart rate of 60 to 100, because the SA node sets it. So that's up in the right atrium. Now when we fire off, or when the SA node, since it's a nodal cell, fires off one of the action potentials, where's it going to go? So the key to understanding this is, in the atria, when we put a shock down on something, like if we were going to stick an electrode in a puddle of water, who would get shocked first? The person standing on this side or the person standing on this side? If they were standing in equal distance to the electrode, both of them would get shocked at the same time, right? It doesn't travel one way faster than the other. It travels both ways equally. And it's the same with this. So when we have this SA node fire off, it's actually kind of right in here, in our right atrium, it's going to send out impulses in all directions. And they're going to propagate in all directions. And as it's moving through all that muscle cell, they're going to fire off and contract. So it kind of propagates out like if you threw a stone in a puddle or a stone in a lake. You get those ripple effects. You get the ripples that move out and get wider and wider and wider until they're gone. It's going to be the same thing here. So this moves out in a ripple effect all the way around, and it's going to contract the whole atria. Our AV node, which is next up in our path of conduction, that's going to be sitting right about between the atria and the ventricles in the middle of the heart, so like in the septum. And I've got it drawn right here without the heart model on it, so this is just the conduction system. We have the AV node, and when that signal reaches it, because we know that it comes out like this, and it's going to move through that heart cells and contract them as it's going along, when it gets to this, it's going to pause for a second. The signal is going to reach the AV node, and there's going to be a slight pause. And that slight pause is important so that all of this atrial tissue or atrial muscle can contract at one time and force blood into the ventricles. If we didn't have this pause and it fired off as soon as it got the signal, well, we wouldn't get the ventricles completely filling up because the atria wouldn't have contracted completely before the ventricles contracted. So we need that. That's important. It's important to have a pause here, but not too long of a pause, as we'll find out. All right, so we got the AV node. After the AV node pauses for a little bit, it's going to send out a signal. And that signal is going to go to a specialized structure called the bundle of His. So the bundle of His is right off the AV node, and it's going to integrate that signal and send it down these two special wires. The two special wires we've got are the right and the left bundle branches. They call them bundle branches, and they're right here. They're going to be running along the septum between the right ventricle and the left ventricle. And they're not going to actually, they're like a wire, a well-insulated wire. They're not going to induce any contraction of the ventricular muscle until they get to the bottom of this, of their branches, okay? So we get to the bottom of both of the ventricles. So it's going to send that signal down. Each of the bundle branches, the right and the left bundle branches, because we've got two, each is going to go to a different wall of the ventricles, the right or the left ventricles. And then when it reaches these Purkinje fibers, that's when the Purkinje fibers have a special type of junctions with all the cardiac myocytes that allow them to actually fire. So what's the impact of that? Well, since we're not getting any conduction in the bundle branches of any muscle firing there, it only starts to tell muscle to contract after it reaches the base of the heart. And then that signal is going to keep traveling up and keep telling all of the cardiac myocytes along it to contract from the bottom up. So that way you can have the ventricles contracting and forcing blood up and out through the aortic and the pulmonic are valves. So we need to contract bottom up. So this system is kind of ingenious because if we went straight down, it would be pushing the muscle, would be contracting and squeezing blood down. Well, we don't have any valves there, so that's not the way we want it to be done, okay? So it's important that we understand each of the different ways that it's conducted. All right, so now that we understand how the electricity is conducted in the heart, now we can move to the waveforms on an EKG paper. So on an EKG paper, we're going to have three main different waveforms. I realize that there's another one, but we don't pay attention to it a lot. So our main one is going to be, our first waveform that we're going to see on an EKG strip is going to be our P wave. So that's right here. And as you can see, the P wave is slight reflection in they call this the isoelectric line, so there's no current moving to or from the lead there. But what that corresponds to is important. So the P wave, when what it is signaling is that the SA node is firing, okay? And when the SA node fires, what's going to happen? All the atria are going to contract. So the P wave corresponds to atrial contraction, okay? And then we have a little bit of a pause here between the P wave and then our next waveform. What does that mean? Well, that means that our SA node is fired and it's gotten to the AV node, and the AV node takes a little bit. It takes a little bit to send that message on to the bundle branch, or to the bundle of His and the bundle branches and the Purkinje fibers. And we said that was because we need time for the atria to completely contract and fill the ventricles. So this, this interval here is important, and we call the time from the start of the P wave to the middle of this complex here, which we'll get to, the PR interval, and it is about 0.12 to 0.2 seconds long. That's going to be important because that's the time needed for the atria to fill the ventricles. All right. So now the next thing we have is our QRS complex. So our QRS complex is named thus because it has like 3 different waves. It has a Q wave, which is the first down deflection in the isoelectric line, and some of our leads might not have this depending on how we're looking at the heart. And then we have an upward deflection when we get the R. So the big pointy thing here is the R. So this is the Q, this is the R, and then we have the S, which is the start of the upward reflection again to our isoelectric line. That corresponds to the ventricles firing, okay? And that makes sense when you think about it, because if you look at this, look kind of what this looks like. We've got a deflection this way, and then up, and then this way. Well, that means, or it looks kind of like, it's bifurcated just like our bundle branches. That's because it's our depolarization of our bundle branches and our depolarization of the Purkinje fibers, which are allowing us to contract our ventricles, okay? So this corresponds, this entire complex corresponds to ventricular depolarization and thus contraction, all right? And then this complex, we have to measure how long it is, otherwise we know something's wrong. If it's too long, we know something's wrong. So the measurement of that is 0.08 to 0.12 seconds. The last waveform that I'm going to talk about is the T wave. This just represents the repolarization of the ventricles in the heart. And that's going to be a quick upward deflection and then back to the isoelectric line. The last interval we have to worry about is our QT interval. So this is the measurement of our Q to our end of our T wave. And that's important because if we get a prolonged one, we can run into some dangerous arrhythmias. The normal interval to that is 0.35 to 0.43 seconds. Simple enough, right? Oh man, I'm running out of time. Okay, so that's all good and well. We have pairs of leads in our 12-lead EKG. So the first 6 leads are the frontal leads. They're going to be looking at the heart from a front pattern, okay? So we've got the 1, 2, 3 AVF, AVR, and AVL, and these leads are computed. They're not actually specific electrodes on our skin, but we'll see. We'll see how it goes, okay? We'll see how it all works out. Let's see how much time I have left here. Minute 16, all right. So the way that she talked about this today was with a triangle, and I think that this is the best way to understand how we're getting the different views of the heart. So I'm gonna pause it here and then start taking a new video so we can stay under 20 minutes, and then we'll pick up with that.